Hello everyone. This presentation is a part of the final project, which is to design a satellite hub. We are Team RAS. Team members are Ashwini, Richa, and Srividya. The outline of the task is as below. First, the design goal, then the assumptions we made during the design of our wireless satellite hub, the design constraints, the design specifications, the working of our modules, and the benchmark measures, and the simulation results we got, and then the final conclusion. The design goal was to design a hub controller that is cheap, that is to achieve a low cost, efficient, and which has an optimal latency. Assumption made during our design is if our memory is full, that is, if all the memory units what we used in our design are full, then hub starts to back up data in the satellite. Then second is data is fetched from the satellite only if it is requested by device, and first in first out is used and is based on FIFO policy. The data is removed from the memory and is stored in the satellite. The design constraints are two devices cannot write to the same tag ID simultaneously, and the hub can handle maximum 3 transactions at a time, that is one per device. The design specifications are the maximum bandwidth of the local wireless hub is 11 megabits per second. Of the satellite link up and down both adds up to 2400 megabits per second. The memory we used in our design are M3 units, which has size of 1 KB, and they are total 10 in number in our design. The latency is M3 takes a read latency of 15 clock cycles, a write latency of 15 clock cycles. The latency of one 16-bit buffer is 1 clock cycle. Latency of satellite for up and down link summed up to 100 clock cycles, and the latency of the data center is 50 clock cycles. Clock timing specification used in the code: 1 clock period equals 10 nanosecond. The time unit precision is 1 nanosecond per 1 picosecond. We have incorporated modular based design approach. All the modules work in pipeline structure, which improves latency in our design. Control registers are used and the code is reusable. The benchmark measures what we got from our design are: the cost of total memory used is $30, as cost of each memory unit is $3, so 10 makes it $30. Latency calculation: consider 128 bytes of data sent from a device. If it starts at time 0, from the simulation result we are getting it at 19606 clock cycles. So the latency we got is 19606 clock cycles. Same, if we are sending one kilobytes of data and it starts at 150 clock cycles, then based on our simulation results we are getting it after 176,300 clock cycles. Therefore the latency we got is 176150 clock cycles. In case of request, if we are requesting 128 bytes of data and if its start time is 20,000 clock cycles, we are getting it after 39,502 clock cycles, which gives us a latency of 19,502 clock cycles. The cost for communication to from satellite is $1 per minute. Therefore for 1 second it's something around $0.016, as we have shown in the slide. Therefore for 1 clock cycle we are getting 1.6 into 10 raised to the minus $10. So total cycles to communicate with satellite will cost up to around $1.4. Hub controller module is shown in the slide. It consists of test bench, which gives the desired signal such as tag info, TS data size, and send request to the device. There are various modules in the hub, like device read write, which store or transmit serial data from or to device. Memory read write module has which has a main memory units, which is 10 for our design. memory buffer to store transmit data parallelly, and control register which gives the required control signal during read-write operation. The block diagram for device to send data. Say let's take for example device 2 is sending 128 bytes. The device receives the required information from the test bench. After the device is selected, like say for example device 2, it sends the data, sends signal to the hub where the device read-write module gets the signal and data stored serially in the device buffer in D for 305 clock cycles as we have shown in our calculation in design specs. From the buffer in D of device read-write module, the data sent by the device is transferred to the second location of the memory buffer. Memory buffer is an array of size 8, each 16 bits wide. The first three locations will store are the device buffers for D1, D2, D3 respectively. The next three locations will have tag info of the three devices, and the remaining two are used for data send and receive from satellite communication. And memory allocate works parallelly with write buffer, that is, during bytes are being transferred in the buffer, the memory allocates search for the empty memory and the start location where the upcoming data from device can be stored and gives the information to memory read-write module which then sends signal to the selected memory and data is stored in the memory.
Here we show the device data sent calculation. From device to hub, single way bandwidth is 5.5 megabits per second. To store 1 bit in buffer, it takes 19 clock cycles. To store 16 bits in buffer, it takes 305 clock cycles. To store 16 bits from buffer to M3, it takes 15 clock cycles as shown in the timing diagram above. So total clock cycles is equal to 305 clock cycles to store 16 bits, that is 2 bytes. Since a parallel operation is supported, write latency is not added in the total data clock cycles.
The slide shows a block diagram for device to receive data from the hub. Let's take for example device 2 is requesting 128 bytes. So from the test bench we are giving the device ID and TS size and the respective send or request signal to select the device and what the device will do, that is send or request. So here it's a request operation. So the device will send the request signal to the hub where in the device read-write module will have the tag info in the device buffer in D which will be given to the module mem read-write and according to tag info in mem read-write it will go to memory M30 location. M30 memory is also used for storing the 64 tag infos. Then the selected tag from M30 is stored in location 5 of memory buffer as we have explained earlier in the previous block diagram. The tag from memory buffer is given to device buffer DIN and the device module communicates with mem read write to give the start address from where the device should start reading the data and the data from that address is sent to memory buffer, location 2 of memory buffer. From location 2 of memory buffer, data is transferred to the device buffer IND and then from device buffer IND it's given to the device serially.
When device makes a request for data, memory loads 16-bit tag in and it takes 16 cycles to do that, and memory parallelly loads data to the memory buffer in 16 clock cycles. From memory buffer to the device, data is sent serially and that takes 304 clock cycles.
The slide shows the block diagram for device to send data to satellite. So when all the memory units in the hub are full, the memory allocate module sends a backup command to satellite read-write module. Then satellite read-write module sends 16-bit command to memory read-write module. The memory read-write module, after receiving the command, instantiates the memory from where data needs to be sent to the satellite, say M31 as an example. The data from M31 16 bits at a time will be then stored at 7th position of the memory buffer as explained before in the description of memory buffer. The data from the memory buffer will then be stored in the satellite read-write buffer from where it will be given to the satellite serially. The same thing happens for device to receive data from the satellite. When device provides a command to receive 1024 bytes, say for example, uh, if the memory is full in hub controller, then 32-bit command is sent to satellite and data is received from the satellite based on sat command control register. The control register gives tag info of the memory whose data needs to be moved to satellite, the tag info of the memory where the data from satellite needs to be moved, and the total byte that to be moved between satellite and memory. Here the calculation we have shown from hub to from satellite, taking single way bandwidth 1200 bits per second. To transfer 1 bit we take 83,000 clock cycles. To transfer 16 bits it take 1328 triple zero clock cycles. To transfer 16 bits to buffer it takes 1 clock cycle, and to store 16 bits from buffer to M3 it takes 15 clock cycle. That is the latency of the memory unit we have used. So total clock cycle sums up to somewhat around 1328166. That's approximate calculations. These are the simulation results for the different traffic files, and here the conclusion. We have achieved reduced latency within the given specification by using pipelining concept and parallelism. The cost of our system is cheap. It's just $30 without compromising on the latency. This is surely a responsive system which is highly cost effective. The following are the benchmark results. Cumulative latency comes approximately 2 into 10 power 8 clock cycles. The communication cost is $1.4 and the unit cost is just $30. Thank you.